In this video, we are going to be talking about the relationship between volume and temperature. This continues our video series on simple gas laws. We are going to be talking about the relationship between volume and temperature. We talked earlier about how temperature is average kinetic energy. So if we take this balloon in an ice water bath, these gas molecules are, on average, moving slow because they're cold, moving slower. And so you can see here the tails are not moving very fast. In this balloon, the number of collisions with the sidewall and external, these are equal and opposite, and so the balloon is at constant pressure. If we take this out of the ice water bath and instead put it in a very warm boiling water bath, then our kinetic energy of the gas molecules inside increases. And so they are moving faster. So you can see here the tails are moving faster. But the external atmosphere has not changed, and the volume of this object is very flexible. And so to maintain a constant pressure, if we're hitting harder, we have to be hitting less frequently in order to have the same pressure on the inside as on the outside. So we are still at constant pressure. So even though we are hitting harder, we are hitting less often by having a volume larger so that those collisions are more spread out. That means that volume increases with increasing temperature. And you can do this type of experiment at home if you like. So here we have our volume and temperature relationship, and you can see that there's different lines here. The different lines represent different amounts of gas. You can see the molar amounts here have changed for these different lines. That gives them different slopes, but they all have that same linear relationship as before. So we have volume is equal to our slope times our temperature. And this is true in all cases. If we extrapolate the lines back, we can see that they also reach this absolute 0 point on the Kelvin scale. So absolute zero is back here. That's the coldest temperature possible. All of our gases will condense into liquids at some point before then, and so their lines back here are dotted because they're just extrapolated back, because they aren't gases at that point anymore. But even so, we can see that this is a nice linear relationship between volume and temperature. This is known as Charles's law. If we take this linear relationship between volume and temperature and solve for the slope k, then we can say at one volume and one temperature, that will be equal to a volume and temperature data point at a later time. So if this is initial and this is final, we can calculate what our final temperature and volume is, knowing the initial. Here's an example problem. It reads, a gas at 89 degrees Celsius occupies a volume of 0.67 liters. At what temperature in degrees Celsius will the volume increase to 1.12 liters? Let's go ahead and identify our variables. I'm going to be looking for initial volume, initial temperature, and then final volume, final temperature. That's like our second data points. I'm just going to use 2's to be consistent with the earlier formula. So liters is an initial, and we always have to remember that our temperature needs to be in Kelvin. and then this is the final volume. And we are searching for that temperature. So if we remember our formula, volume and temperature are also directly proportional. Since if we increase volume, we're increasing temperature, so they are directly proportional to one another. We are solving for T2, so T2 will be equal to V2 divided by V1 times T1. So I multiplied by the reciprocal on both sides in order to cancel out everything over here. And then I multiplied both sides by T2 in order to get this T2 out of the denominator. So I was left with V2 times T1 over V1. And so that is going to be 1.12 liters. And then my initial temperature is 362.15 Kelvin. And then my initial volume is 0.67 liters. So there's my initial volume. So now I gotta type that all into my calculator so I can end up with T2 is equal 1.12 times 362.15 divided by 0.67. And so I calculated 605.38. I'm going to need just 2 sig figs, so only those first two are significant. But I need to convert this back into Celsius because that's what the question asked for. So I need to subtract 273.15 from that in order to get my Celsius temperature. And so that is 332.23 Kelvin with, not Kelvin, Celsius. I just converted you back into Celsius. And so that is going to be T2 is equal to 330 degrees Celsius. Let's do a conceptual double check. Since our volume is increasing, our temperature should also be increasing. So I looked at the volumes here. Volume's increasing, temperature should be increasing, so my final temperature should be more than 89 degrees Celsius, which it is. Here's a practice problem for you. Go ahead and pause the video and try to work out this problem on your own, and then unpause the video when you're ready to continue. Alright, let's go over this. It says a volume is filled with 600 milliliters of air. Milliliters is a volume unit. And at 20 degrees Celsius, that is a temperature unit. What is the volume at 60 degrees Celsius? So that is my final temperature. And then it's asking for volume. And so that is my question mark. So given my equation, I am solving for V2. So that's the variable I'm trying to isolate. I'm going to multiply both sides by T2 in order to eliminate T2 on this side of the equation. So now I can flip that equation around. So V2 is going to be equal to V1, which is 600 milliliters. Remember, it doesn't matter what unit your volume is in, as long as your two volume units match. So that if you have milliliters here, you're going to get your second volume in milliliters. My T2 is equal to 60 degrees Celsius, so I'm going to need to convert that into Kelvin. And then my T1 is going to be in the denominator, which is going to be 20 plus 273.15. So you can see here that the 273.15s do not cancel out because they are added, and math doesn't let you do that. So that's why it's important to do your conversions into Celsius before typing this in. I am just going to use parentheses to make sure that I'm communicating with my calculator to make sure that it does the conversion before doing the multiplication and division. And so that is 681.869. This is going to be significant to the tenths place because I didn't write the tenths place. So it's going to be significant to the tenths place, which is here. This is also going to be significant to the tenths place here. So both of those are going to have 4 sig figs. That's going to have 4 sig figs. So I'm going to need 4 sig figs. And so that's going to be 681.9 milliliters. We can also do our conceptual double check. Since our temperature is increasing, that means our volume should be increasing. So that means our second volume here, our volume needs to be more than our first volume. So V2 should be more than V1. And it is.